Artificial intelligence seems to be everywhere these days, right? It's doing things that honestly feel a little bit like magic. But here's the crazy part. What if I told you that all of this incredible technology, from a super complex AI to the very device you're watching this on, is built on a foundation of just two incredibly simple ideas, on and off. That's it. So let's dive in and really peel back the curtain to see how it all actually works.
So to kick things off, we're going to see just how powerful and, how silly a few lines of code can actually be. This quote from Harvard's David Malan perfectly sets the stage for a little experiment that, trust me, reveals a massive truth about programming.
Okay, so here's the setup. The professor, he uses this super popular programming language, Python, to write a tiny program like just a handful of lines that connects to an AI service from a company called OpenAI. The whole goal is just to create his own little custom chatbot.
So he runs the program, right? And he asks it a pretty simple question. What is CS50? The AI does its thing, connects to the service, thinks for a second, and sends back a totally normal, totally accurate description of Harvard's big Intro to Computer Science course. So far, so good.
But then he does something interesting. Before his next question, he adds just one new instruction. And this isn't a question for the chatbot. It's a command to the system itself. And the command is as simple as it is ridiculous. Pretend you're a cat.
So, with that one little rule now in the system's brain, he asks the exact same question as before. What is CS50? Nothing about the question has changed, but the AI's entire personality has just been given a brand new directive.
And there you have it. The AI gives the same correct answer, but it tacks on, well, a little something extra at the end. And this is the mind-blowing part. A single, plain English sentence was enough to make this gigantic, multi-billion-dollar AI model just meow.
I mean, how is that even possible? It feels like pure magic, right? But it's not. It's all about something surprisingly simple, just breaking down a big problem into a bunch of clear, logical steps.
Okay, to really get this, let's go old school. Think about finding a name in one of those huge, massive phone books. This physical problem is actually the perfect way to understand how computers think. Those step-by-step instructions, that's what we call an algorithm.
All right, so there are a couple of ways you could tackle this, right? First, there's the slow way. You start at page 1 and just flip page by page. I mean, it works, you'll get there eventually, but man, is it slow. But then there's the smart way. You rip the book open right to the middle, figure out if your name is in the first half or the second, and you literally throw away the half you don't need.
So let's walk through that smart way, that algorithm. Step 1, go to the middle. Step 2, ask a really simple yes or no question. Is the name in this half or that half? Step 3, chuck the half you don't need. And then you just do it all over again with the smaller stack.
And here's where it gets really wild. Look at the difference. To find one name in a 1,000-page book, the page-by-page method could take, on average, something like 500 steps. 500! But our tear-it-in-half method, it takes about 10 steps. That's it. 10. It's not just a little faster, it's in a whole different league. That's the power of a really good algorithm.
Okay, so we get it. A computer follows a set of steps, an algorithm. But wait a minute, how does a box of wires and silicon even understand what a step is? The answer is ridiculously simple.
It all comes down to a language called binary. See, at its most basic level, your computer is just billions and billions of tiny little switches. And a switch can only do two things. It can be off, which we'll call a 0, or it can be on, which we'll call a 1. And that's it, seriously. Every single thing a computer does boils down to patterns of those zeros and ones.
Imagine a row of light bulbs, okay? If we want to represent the number 1, easy. We just turn on the first bulb on the right.
But what about the number 2? You might think we just turn on a second bulb, but nope. It's a bit more clever. Just like with our numbers, the ones, tens, and hundreds place. Well, here, the position of the light bulb is everything. To make a 2, we turn the first bulb off and turn on the second one. That second spot is the 2's place.
So how do we get to 3? Well, it's just simple addition. We turn on the 2's place bulb and we turn on the 1's place bulb. 2 plus 1 gives us 3. Using this pattern, we can represent any number we can think of. So here's the kicker. With just 8 of these light bulbs, or what we call 8 bits, you can create 256 different patterns. That lets you represent every number from 0 all the way up to 255. And a group of 8 bits is so important, we gave it a special name, a byte. You've probably heard that word before.
Okay, so we figured out how to represent numbers using on and off switches. Great. But how do we get from numbers to, words, pictures, cat videos, everything else? Well, it turns out if we can represent numbers, and we can all just agree on what those numbers mean, we can represent literally anything.
So, way back when, a bunch of smart people got together and created a standard called ASCII. Think of it like a universal secret decoder ring. They just decided that the number 72 would stand for a capital H. The number 73 would be a capital I. So when you text hi, your phone isn't really sending letters. It's sending a sequence of numbers, 72, 73, and for the exclamation point, 33.
And this is so important, context is everything, because those exact same numbers, let's say 72, 23, and 33, could mean something completely different somewhere else. If you open up a photo editor, that program might not see letters at all. It might see those numbers as the recipe for a color. 72 parts red, 23 parts green, and 33 parts blue to make one single dot of color on your screen. The zeros and ones are identical, but what they mean totally changes.
All right, let's zoom back out and pull all this together. We started with a chatbot that says meow, and we've gone all the way down to the tiny little on-off switches that make the whole thing work. What we've been doing is peeling back the layers of what's called abstraction. See, at the very, very bottom, you've got the physical hardware, the zeros and ones. On top of that, we build a system like ASCII to turn those numbers into letters. Then we use algorithms, those smart recipes, to manipulate those letters and numbers. And then way up at the top, we can finally build these amazing tools like an AI chatbot. Each layer just builds on the one below it, hiding the complexity. And that right there is why understanding this stuff is so empowering. Because even as AI gets smarter and more powerful, knowing how these layers work is what keeps you in the driver's seat. You're the one giving the instructions. You're the one with the creative ideas. At the end of the day, computer science isn't really about memorizing code. It's about a way of thinking. It's about solving problems. And in a world where AI can do almost anything we ask, the real superpower is knowing how to ask, how to think, how to solve the problem. So the real question is, are you ready to take the wheel?